Good morning, ladies and gentlemen. Good morning. We are again in the course of advanced quantum mechanics, and we're about to get a half of it. Time goes very fast. Uh, as far as lectures are concerned, now we start with the lecture number 6. And we switch our gears. We go for something else. So far, we've been dealing with particles. We have started with identical particles, and we have second quantization. We clean up, we look at some examples, and we have reached kind of a summit, I would say. Starting from particles. But we know at their summit we have quantum fields, which are neither fields nor particles. That's why it is constructive, also from physical point of view, to get to the same summit by other paths, just starting from the valley. So instead of particles, we start with fields. We will be talking about fields for a while, and that would be exceptional lecture. I won't talk about quantum mechanics at all. Today we'll talk about classical fields. I have a message. I will put it here very soon. But let me tell you what we will be doing. Of all things, we will be busy with a chain of balls connected by springs. We will consider oscillations in a chain of such balls. We will generalize it to elastic string. And we will, as example of this simple model, we will understand that the field and eventually any field, classical field, can be seen as a set of harmonic oscillators. That's important technical part of the message. All right. Then we turn to another example, and that would be an example which is usually treated in advanced quantum mechanics courses, in the course of field quantization, very important from practical point of view. Sure. Well, I will formulate Maxwell equation, and we will talk about vector and scalar potential, gauges. I don't know if you remember gauges from your electromagnetism course. There will be a chance to repeat it. Right, and finally we got to the same message that also electromagnetic field can be seen as a set of harmonic oscillators. Making such incredible job for the whole field, we will finish with an example of a single oscillator, something which consists of capacitance and inductance. And well, you know, if you do this, you just have a one mode oscillator, and we do precisely the same job over there. Fine. If I put it like this, the whole lecture seems a bit boring. We just take different examples, do something, and conclude with the same concept. Right, sure. That's why I guess I better formulate the message. Why do we do so? Okay, First of all, let us understand what is a classical field. By definition, it is some physical quantity which varies from point to point in space and has some time evolution. So symbolically I write it like this. There is a vector, there's a field A. A stands for arbitrary, which can also have some indices, for instance, vector indices. We can talk about electric and magnetic field in a medium. We can talk about stress in an elastic medium. We can talk about displacements of elastic string. We can talk about waves at ocean surface. We can talk eventually about almost everything which we see in this world. Most of physical systems at classical level are characterized in this way. Yeah. For the time being, I assume no dissipation, which means that the fields would obey some Hamiltonian dynamics. There will be some energy, and they will oscillate according to Hamiltonian without any dissipation. First of all, it looks a crucial assumption. But when we talk finally about dissipation, which we do in lectures number 10 and 11, we will understand that in fact it's not that bad, it's not crucial. So it's no problem to describe dissipation within the same on the same footing. All right. As such, these fields obey time-dependent equations coming from the Hamiltonian. There are fields, kind of roughly, there are two cases. Yeah, like if you go to downtown, there is a chance to meet a dinosaur or a chance not to meet dinosaur. There are also only two cases. In this way, all fields can be separated in two classes, right? Linear fields and nonlinear fields. Non-linear fields are nice. There are linear equations which can be solved very quickly for a very big number of variables. Non-linear fields are nasty and interesting. What is the point that eventually any field, if you consider small deviations from equilibrium, can be linearized. So one can linearize these time-dependent equations, and one would end up with a linear theory. Good. And finally, the message. Finally, the message, and the message is that any field, any physical quantity under these conditions, we can bring to a standard form. We can regard this field as a set of independent oscillators. Since we are talking about a system with infinitely many degrees of freedom, there are infinitely many points in the space, right? That has to be infinite set. Oh, so what if if the field is linear? There's no problem with this. We can operate with each element of the set separately. Fine, so this is a message which looks a bit technical. The power of this message is that this fact enables quantization of the field and eventually any field. We can quantize electromagnetic field. We could also quantize ocean waves in very same manner if because we can quantize a single harmonic oscillator. Fine. So that's why I pay so much attention to this. That's why I pay so much attention to generality. Since fields is almost everything which we see in this world, we can quantize almost everything if it's needed. For ocean waves, quantum effects are perhaps not that relevant. For electromagnetic fields, they are. And okay, we will go through all steps of this. Right. So, are there any questions about this lecture, about this message? So please put them to the chat. As usual, I would be delighted to talk about this. Fine. No questions. And the appointment is that if there are no questions, I ask questions myself. Sir, I would like you to come with an example of a field satisfying these conditions, which I have not mentioned yet. Classical field quantity, which depends on space and time, which I have not mentioned yet. Curvature of space-time. Wow. Gravitational field. Wow. I'm really pleased. Yeah. I still remember times where here at this technical university, there were courses about general relativity. Now they extinct, but well, perhaps it's time to get one running. Yes, it's a valid example. Oh, Coulomb potential, yeah, it is yeah, related to electromagnetic field, I would say. It's electrostatic potential. Good. So let us go further. I'll start with examples of the fields, and just to illustrate, look, it's not really theory. It's kind of life. Hmm? If you want to be practical, you can put it as engineering problem. You have some system, and the task is to describe the system, to understand the system, the oscillations in the system, so how to make a Hamiltonian and present it as a set of harmonic oscillators. All right, so let's take such a system. We can make it with our hands. It's a chain of balls which are connected by springs. Good, so there's some equilibrium position. All balls are on the same distance. And I choose coordinates for each ball that x1 is a deviation from this equilibrium position. So in fact, I've linearized. In fact, I have to linearize because you understand that if I pull the spring too much, it won't be that elastic. So I'd rather consider small deviations from relative positions. Fine. So how to make a Hamiltonian? I've n balls with masses m. That sets a kinetic part of the Hamiltonian. Now I have to think of potential energy, and right, what I note is that each spring is between two balls, and the deformation of the spring is proportional to the difference of two coordinates, right? For nearest neighbors. Potential energy is a square root of deformation with some coefficient, right? So I write this as well. Good. It's I would say it's a creative part, although it's pretty straightforward, but at least you do something. The rest is in modern physics pretty much automated. If I have a Hamiltonian, I immediately write down equations of motion. And for any Hamiltonian, they go in the same way. Look, this is equation for derivative of x. This is equation for derivative of momentum. Right, so general equations, and to get it right, I need a concrete Hamiltonian, which I have above, right? So I understand that velocities just given by momentum of corresponding particles divided by masses. That was pretty much obvious. Let me concentrate on this. Yeah, in fact, yeah. Derivative of the momentum is a force acting on a certain ball. And I understand that each ball feels to nearest neighbors. Those, if I look at the ball n, it feels n plus 1 and minus 1. All right, obvious because each ball is connected to two springs. Fine. It sets two equations. Let's go fast. Let's make one equation from this two. And to this end, just differentiate this equation twice. So I have time derivative of momentum. I get force here. Here we are. Momenta are gone from this equation. We have only coordinates. Ooh, we still have plenty of coordinates to carry about. And what helps is the assumption that the system is uniform, that all balls are the same and all springs are the same. Then it's homogeneous system. And for homogeneous system, I can easily write a solution in terms of, you won't be surprised, in terms of plane phase. Sure, I could do it pretty constructively. I just have a guess that there is a solution of this kind. I want to have a single exponent corresponding to wave vector k, and some frequency. I don't know the frequency yet. Well, but x is a real variable. So I need to add something complex conjugate to it. But since equations are linear, I can treat this term separately. I can, for instance, substitute only the first one, only this one. Well, okay. Then what does it give to me? That gives me second derivative of UK, and the second derivative would come with frequency, right? If I put it here, let me see. I need to understand how the exponent transforms if I shift n by +1 or -1. So here have 2. No transformation here have exponents. Let us see, ik shift by n+1. Here we have exponents minus I k. Right, I bring these terms together and well, managed to figure out the frequency. So for each wave vector in this chain, there is a solution which oscillates with certain frequency. Here's the frequency. Good. Then I would like to have all solutions. I want to have general solution, just for completeness. I want quantize. I want to quantization is not in our schedule for today, but in principle I want to quantize fields. So I want to quantize all fields, all field configurations. So I look at general solution. To get a general solution, I want to understand what are all possible cases in order not to miss one. Good. So let me assume periodic boundary condition for n balls. I'm kind of making a big ring out of this chain of springs. Then after n balls, all the exponents have to be the same owing to periodicity. That sets possible case defined in this way. Good. What's the outcome? I have general solution for this chain of springs, oscillations with different frequencies, different phase vectors, whatever. It can be rather complex. But since the system is linear, all these terms just oscillate on their own without interfering with each other. Yeah, yes, case quantized. Case quantized, but simultaneously it is an interval between minus and plus pi. Just quantization is inverse, kind of distance between the neighboring case is proportional to 1 over n. Fine. Let us see. That's nice to have general solution. I would like to consider something else. Why is it true? Because our space and time is continuous, And I want to show that the same method eventually works for continuous systems as well. All right. So this is the Hamiltonian. In this case, I kind of take elastic string, and yeah, now it oscillates in this direction, and U is deviation in perpendicular direction. But anyway, there is the same kinetic energy and potential energy. What do I do with kinetic energy? I consider elements as moles, and in fact, I sum up over the elements. That's what I get. Dx divided by density per unit length is just the mass, inverse mass of the ball. Right, and it is also potential energy. I do this as a limiting transition in this equation. This looks pretty much like second derivative squared. I put it here. Fine, sir, I can derive equations of motion. Instead of differentiation, I vary over these quantities, but yeah, it's my nuisance, I would say. One can always discretize this system and work with discrete variables, but it's not necessary. That's why I write it like this. So this is equation for U. This is equation which is coordinating. This is equation for momentum. They have the same structure. I substitute concrete Hamiltonian. I got these equations, and right, I combine it in together. What I get is wave equation. So that omega is directly proportional to the wave vector. In distinction from this, here I have some complex function, well, sinus. And here in this limit and continuous limit, it's just proportional to k vector. Fine. So with this, I can write down general solution. First, A solution. There is for each k, I got certain frequency of oscillations and certain amplitude corresponding to the amplitude of this particular wave. There was a question why is it a small delta in front of h? I believe you mean this formula, and this is just a sign of derivative. I write it in this fancy way because I vary continuous quantities. But if I would discretize it, it would be just derivative of the Hamiltonian over momentum of a particular element of the string. So it is just the same what I put here. Fine. All right, so for each k we have, as I said, certain solution. Right, general solution. General solution is here. And I will pay attention to the fact that despite that we are in continuous limit, K remains quantized. Now it doesn't go from in the interval from 0 to pi. K can take any values, but still there is a quantization with a quantization step proportional now to the full length of the string. So quantization of K remains. Which means I really can count all possible solutions, all modes which I have in a finite string. Good. And as I promised, we are not satisfied with the fact that we have solved everything, that we have general solutions. We would like to get it as a set of independent oscillators. To this end, I would like to transform the coordinates. So instead of obvious coordinates, which are amplitudes of all possible solutions, I'd like to introduce some this, and that comes with an ugly square root. Ugly square roots actually belong to quantization business, but yeah, we don't quantize it, but we are pretty close to it. Why do I choose this ugly square root factors? I'd like to get the Hamiltonian to a standard form in such a way that the frequencies that coefficients in this Hamiltonian are frequencies only. Right. It also saw that in these coordinates, one of the reasons to go to these coordinates is that they have a very simple time dependence. Time dependence corresponding to the same frequency. Right, how to see that? Well, you just get here the general solution. So at any k, it oscillates with a certain frequency. Deviation oscillates with certain frequency. Fine. Now, this D is complex, which means that we have two real variables. So let us consider convenient equivalent and convenient representation. And let us introduce variables which are proportional to a real part of D and imaginary part of D. Again, I've got some ugly square roots, which I personally find difficult to remember. I have to recalculate it every time and you. Again, these ugly factors are there for a good reason. If I now express it back, if I express these in terms of P and Q, and substitute it to this Hamiltonian, that's the form I get. Again, I can do it for each mode, for each operator set. And here we are. And that looks pretty much as the Hamiltonian of mechanical oscillator. Apart from the fact that P does have the dimension momentum and Q doesn't have to have dimension of coordinate, but the structure is the same. There's a P squared for kinetic energy, there's a Q squared for potential energy. And these quantities are called generalized ones. Generalized momentum, generalized coordinate. Fine. They obey, since we have Hamiltonian, they obey the same equations which I've written before, same linear equations. Good. So we did it. We kind of know the goal. So where is the string? Where is information about the fact that we have quantized a string and not ocean waves and not eventually a chain of springs? Eventually, all is hidden in this coefficient. So D is a variable which is general, which is the same for all possible oscillators. For our oscillator, we are interested in displacement. We care about U, and all information about the string goes here. And also in the dispersion law, in a concrete dependence of omega on K. Good. So let us see. It looks like we are ready for electromagnetic field. So let me start with electromagnetic field. Let me recite what we commonly call Maxwell equations. So here's Maxwell, and he was a good experimentalist, splendid experimentalist, but I guess we won't know him if he wouldn't have written a book. So at some stage, he decided to tell to the world everything which he knows about electricity. Electricity and magnetism was very active research topic by the time. So he has written a book with main equations, and eventually he counted 54 main equations of electrodynamics, which made it impossible to teach the subject to students. So people did everything in order to reduce this number of equations. And at some stage, and this is kind of, that was a consensus. If it were one equation, it would be too easy to teach. 4, it's just about the same. But what we need 4 equations. It is a little bit consensus. Very soon we will reduce these equations to two without losing anything. And if we consider relativistic electrodynamics, they just have a single equation, single tensor equations for a tensor, which is at the same time electric and magnetic field. Good, but that's custom to talk about Maxwell equations. And what do I want to tell you about this? First of all, although it's not really easy to see. No, okay. First things first. First, these are equations for two quantities, for two vector quantities, electric and magnetic field, which are defined, which are fields, which are defined in each point of space and depend on time. So they satisfy our definition of the field. Second, although it's kind of not quite easy to see from Maxwell equations. Those are evolution equations. In fact, having a configuration of electric and magnetic field, you know how does it evolve in future? You know the derivatives of the field. Yeah, here it is. We have found derivative of magnetic field. And here, somewhere hidden in the end of the equation, we have derivative of electric field. Sure, indeed, we have evolution equations. Right, so we have four equations for two derivatives, which looks a bit much, but this is as a structure. So only first and second equation are time dependent. What is also important to know about these equations? Although these equations can be solved in empty medium without any charges and currents, formally, and it is the most practical way, formally, they describe a reaction on the sources of the field. What are the sources? Sources are electric charge, and the sources are electric currents. Kind of roughly, if I look at it, charge is a source of electric field and current is a source of magnetic field. Right. What is that? Owing to legal reasons, I had to present these equations in terrible French invention, which is called System International. I don't know by which evil doing it became legal in most countries, but it's indeed sure. The law apparently endorses the use of System International in the education. I can see it from the fact that I have this strange, I would say, even say idiotic quantities, mu naught, epsilon naught, which are whatever, something related to vacuum. I never managed to understand this because I personally did it in logical way. And let me make something illegal for you. Don't tell everybody. I will write the same equations, so just flash it in the CGS system in Gauss notations. Then it gets logical. There are no unphysical constants coming. What comes and what is important property of this equation, important constant which determines this is a speed of light. Speed of light, right? Which in System International is composed of this mu naught epsilon naught. Good. So there is also a way to write these equations in a logical manner. Fine. So let me keep master equation, Maxwell equations. I guess it's a time for break. So let's have a 7-minute break if you don't mind at this point. Perhaps I still can find coffee somewhere. So we're coming back after the break. We look again at Maxwell equations. Good. Right. Let me stop with illegal things. Okay, there's a question about Maxwell equation. Where does the factor 4 pi comes from? Factor 4 pi here, one can say just for convenience, that guarantees that the potential from the point-like charge, potential which is gradient of electric field, is charge divided by distance. And not charge divided by distance, but for pi epsilon naught, I don't know what they put in System International. Look, I for 40 years of giving courses, I haven't managed to memorize what did they put in System International. No, I'm mocking, of course, but it really irritates me. This 4 pi was chosen in order to have convenient expression for electrostatic potential of point-like charge. Fine. Yeah, I agree that it at first sight it looks ugly, but as all ugly things, it has a good reason. Right. What I want to say about Maxwell equations. First of all, useful relations. One this relation is most useful because it kind of solves the question of observability of electric and magnetic field. We can only detect these fields by looking at the force which are experienced by charges, in particular moving charges. So there is force coming from electric field, and if charge moves, it also experiences Lorentz force. Right. This is non-relativistic and non-relativistic equation. I must warn you. So velocity is much smaller than speed of light. Right, that is about observability. What we will need soon is the energy density. We will need it because we want a Hamiltonian. right? So there is energy density associated with the magnetic field, electric and magnetic field. So I kind of find it convenient to think of capacitances and inductances. So if you have capacitor, there is a field between two plates, and that accumulates some electrostatic energy. I can wind the coil, put current, there is magnetic field inside the coil. Here it is. It also has some energy accumulated in vacuum. Well, rather fancy. People in 19th century have been immensely surprised. But anyway, it's a fact, so the people get used to it. Fine. A little bit more relations. We also would like to talk about Poynting vector, which is energy flux associated with electromagnetic field. All right, it's cross product of two vectors, electric and magnetic field. Right, when I was a student, I always thought it's Poynting vector, a vector which points somewhere. But in course of examination, they explained me that it's not really so. It is spelled differently. Fine. With this, we can check that Maxwell equations are reasonable. We can run a foolproof take on these equations. How? In this, we have an expressions for energy and for flux of energy. We can prove energy conservation. Right, so how we do this, we express U and we take U, we take S, they express it in terms of electric and magnetic fields. Then we substitute derivatives, which come here, and show that for any field configuration, this is zero, energy is conserved. Which is more important, and sometimes it's difficult to see from Maxwell equations. Sometimes people forgot it, and eventually there are many. If one kind of if you want to come complicate a simple thing, you make a paradox out of that. Yet before university, I was trying to learn electromagnetism by myself, and I got a book of Professor Cooper, and I was totally astonished. I thought I have to quit physics because I didn't understand this. There was a set of paradoxes. But all these paradoxes can be easily solved if one understands that Maxwell equations are in fact faulty. What is a fault? Let me get perhaps back. It doesn't want to go. To these equations, whatever in System International. They're supposed to be, they're supposed to describe a reaction on sources, charge and flux and current. But they do not. They don't serve the purpose because in principle, I could try to put arbitrary sources. But for arbitrary sources, there is no solution of Maxwell equation. It works only if these sources satisfy additional equation. So one, in other words, one can exclude electric and magnetic field from Maxwell equation and get something on sources, which is usually crazy, but it yeah, manifests a fundamental fact. It manifests charge conservation. So Maxwell equations are faulty in the sense that they would not be able to describe electric and magnetic field, which are produced by non-conserving charges. And well, as I said, yeah, perhaps I could give. I wouldn't give you a reference to the textbook of Professor Cooper, but I guess it's contagious because I guess it's contagious. It could spoil your minds, but one can build up plenty of nice paradoxes if one would permit these equations not to hold. Good. Charge configuration, it actually follows from equation 2 and 3 of master equations. Fine. Good. Then I want to talk about again a thing which looks technical, which sought to be technical in the 19th century, but which appears to be fundamental, which appears to be very much instructive in our understanding of physics of electromagnetism and physics in general. I will talk about a vector and scalar potential. Scalar potential, I guess everybody knows, everybody understands, potential, gradient of potentials, electric field. I always wonder is if vector potential kind of is on the same footing for modern generation of the students. So please confess. If you never heard of vector potential, you should have heard of. If you don't remember what the vector potential is, please put no to the chat. And don't hesitate. It's not an implicit attempt to evaluate your knowledge. Just to check. Fine. So how should I start the story in this case? We have electric field and magnetic field. Well, for electric field, we pretty much know that electrostatic potential is very convenient. It just gives potential energy of the charge. You differentiate it, you get force, which is electric field. It's all known, which is less obvious that we could also describe magnetic field if we introduce another quantity, vector quantity, which is called vector potential A. Right. And at the moment, let's treat it technically like 19th century physicists did. Let us just consider formal substitution. I just get a hunch that magnetic field I can represent as a curl of vector potential. And the electric field, okay, that looks ugly again. Why would we have time derivative of vector potential after all? Okay, but it's there. Otherwise, Maxwell equations um, uh, won't be present. Fine. And again, it gives a great technical advantage because instead of 4 equations, 4, we get only 2. If we make such a substitution, the equations 1 and 4 are satisfied automatically, right? We don't care about these equations anymore. We have 2 equations for a scalar quantity and a vector quantity. Here they are. Scalar equation, vector equation. It's still faulty. It will work only if charges and currents satisfy charge conservation condition. Yeah, but okay, you see, it just became more logical. We have 2 equations corresponding to 2 quantities, electric and magnetic field, and these sources just stay in their place. Scalar source for scalar equation, vector source for a vector equation. Fine. So technically that worked. We've got just simple equations. We have less equations. We could enjoy it. The point is that it eventually brings serious philosophical problems, if you wish. These quantities, a vector and scalar potential, are decisively unphysical. There is no device, there is no applicants to measure these quantities. One cannot measure potential or vector potential. One can make a measure only the fields, which are differences, yeah, gradients of this potential. Right. My favorite example that if you have a wire with a voltage of, I don't know, 10,000 volts, you can touch it, you don't feel anything. You need to take another wire with another hand to really feel something, right? In this way, you will feel potential difference between these wires with your whole body, but you cannot feel a potential. The same with vector potentials. So it is a bit crazy. We are physicists. We don't want to have any spirits in our science. We are rational. But in fact, we use unphysical quantities to describe very physical schemes. Right, there are there are several reasons for that. Some reasons are very practical, um, because we just got simple mass, simple structures, equations. We can solve them more efficiently. We can think about these equations in more efficient ways. We can make new devices out of that. Similar reasons that with this we can easily to make a reasonable Hamiltonian for electromagnetic field and for electromagnetic field in with charges. But kind of for me at least a real reason that this kind of reveals very deep pictures in theory. Eventually the theory is such, the world is such that these unphysical quantities are really needed to describe physical ones. With quantum mechanics, we perhaps have more unphysical quantities. Yeah, wave function is unphysical. One cannot measure it in single shot. Nevertheless, it exists. It's useful for the description. Right. Question of Sarah. What about the Aronoff-Bohm effect? Can we see that as measuring the potential? Or would you say that we are still actually measuring fields? At the moment, we are okay. Simpler answer to this question is to say that we are at the moment in the realm of classical physics. And in the realm of classical physics, there is no quantum interference. And quantum interference is eventually Aronoff-Bohm effect. And that's why Aronoff-Bohm effect is so peculiar, because indeed it will show the presence of electric and magnetic fields, not locally, but somewhere. If yeah, perhaps I should recall Aronoff-Bohm effect here. Suppose you have a coil in this direction. There's some magnetic field in the coil, but nothing comes out of the coil, right? And if we consider electron wave, which can go either above the coil or below the coil, if one can consider interference, if one looks at the interference of these two electronic waves, there is a contribution to this interference phase, which is proportional to the full flux in the coil. So although there is no magnetic field which inflects this particle trajectory, there is vector potential outside. Yeah. And that produces a measured effect. So in quantum mechanics, it is uneasy. But in classical physics, such effect doesn't exist. Nevertheless, these unphysical quantities are not quantum mechanical. They also persist in quantum physics, in classical physics, and are useful in this context. Fine. Okay, so let's use these variables. But then then we are forced to think about things which we usually don't want to know. Well, because we feel safe, let me put it frankly, we feel safe in a world which does not give us any choices. That's the best way to achieve happiness. Believe me. Real happiness is that when you don't have any choices, when you don't have any choice, and just follow the crowd. A very efficient way to get happy. You can be happy in whatever while being oppressed. You can be happy in concentration, desk camp, everywhere. Just recognize that you don't have choice. The necessity to make choices usually makes us unhappy. We are afraid to make a wrong choice, whatever. We don't want to do this job. Right. We do because we understand that you choose and it becomes good. Or it becomes bad, you can take another choice. We do choices. But it's is always a little bit unpleasant feeling, right? And the fact that we decided to deal with this in physical quantities um, lead us to the fact that we have to make choices, which is called a gauge. And I shall talk about gauge invariance. What is this? One can choose these potentials in a different in a variety of different ways. If we have one configuration described by A and phi, one can take arbitrary function of time and coordinate, which is called chi, add gradients of chi to vector potential, add time derivative of chi to scalar potential, and fields, master equations, sorry, Maxwell equations, fields, they all remain the same. So a physical situation will be precisely the same. Right, good. Then, if you are about solving problems, you go with this and you understand that some gauges are very convenient for solving your problem, some are not. In this case, you can make a choice of convenient gauge. Right, but the reason for that the results do not depend on a particular gauge. So there was gauge invariance, which is at this stage classical physics looks like um, just a freedom of choice, which might be nuisance, but it will become an issue. It will become really important if you go to quantum particles, and we eventually understand that gauge invariance defines the way the particles interact with electron charges. Fine. Let's look at several gauges. Since many clever people thought about this, these gauges have names. Lorentz gauge. You might think it's yet another typo in my transparency, and that has to be a Lorentz gauge. Lorentz from Leider. Yeah, it's not a mistake, as but somehow Lorentz was also um, in the same business. So in fact, this Lorentz gauge is Lorentz invariant. Yeah, but yeah, for some reasons, Lawrence was Dane, and while Lawrence was Dutch. Right. So, what is the gauge? This gauge is set by the following equation. Right. We say that divergence of vector potential is related to time dependence of scalar potential. Okay, if we do so, we end up with very nice, obvious, easy to remember equations. All right, that funny squared in the left side of the equations, it's called the Lambertian, and it's an operator of wave equation. We have seen wave equation in the beginning of this lecture. It has the same form. Second derivative of time, second derivative of coordinate, and velocity comes into the play. the Lambertian. Fine. So the equations are more than logical. Right, and they are, as I said, Lorentz invariants, because they're invariant with respect to Lorentz transformations with respect to special relativity. So it's very good to describe relativistic fields in this way. The point is that we're not in relativistic world, right? So the charges which we see around, which are in our bodies everywhere, in molecules, they move slowly. They move slowly, much slower than the speed of light. That's why it is better to understand our world on non-relativistic footing. So eventually our choice would be Coulomb gauge. And Coulomb gauge is said by this equation, so vector A is not divergent. Divergency of A is zero. Fine. So there are equations. And the scalar potential, which is conveniently expressed through charge density only, that's fine. And in fact, there is no retardation in this equation. And this is a little bit more complex equation for vector potential, which has all waves around. Good. But this is crazy. In a sense that it contradicts to Albert Einstein, who is the greatest authority in physics. Look, no retardation. So we have a charge. We measure potential here. We shift the charge and we sit in a neighboring galaxy and we momentarily see the change of the potential. Seems to be crazy. So who can explain why it is still valid? It is a field. Yeah. It is a field. It is a field to look at. Let me decrypt the first phrases here. And indeed, the potential is not retarded, but you cannot measure the potential, as I already said. One can measure, as I already said, one can measure only the field. And the field, if you substitute it, compute the field, the fields do show retardation. Very good, correct it. But it's also convenient to have scalar potential which doesn't experience relativistic retardation, and we will use it when we talk about interaction with electromagnetic field. In the rest of the lecture, we do write that. From what I said, which is a standard outline of master equations, we don't yet see that electromagnetic field has anything to do with mechanical oscillators, with classical oscillators. And right, we have to do this. We have to do this job. And as I promised in the beginning of the lecture, I will finish with an example of a single oscillator. Right. As we did for elastic string, we want to find all solutions of Maxwell equations. And eventually we could do it in any gauge. But to speed up the process, let us consider free field. There's no charges whatsoever. And we implement Coulomb gauge. That makes things simple. There is no electrostatic potential, at all for this field. So free field, we can represent solely in terms of vector potential. Good. Then this vector potential satisfies wave equation. The Lombardian is 0. Okay, to remind, fields are expressed in terms of this potential. Good. We want to have all solutions, so we need all possible cases. We should be able to count all possible wave vectors. So we impose periodic boundary conditions. Right. Let us look at partial solutions of Maxwell equation. Right. We look at the solution in the form of plane wave. And okay, frequency that we know. Frequency just frequency of light, wave vector times speed of light. All waves propagate with the same speed with the light velocity, speed of light. Fine. Then at a given k, which is now promoted to vector, right? We are in 3 dimensions. For a given k, a partial solution looks like this. Okay, so we have this exponent. We understand that we need to add conjugated exponent because A is a real quantity. That's fine. Those are amplitudes of the waves. Here I've found something to talk about. Here is a vector which describes polarization. Indeed, some vector quantity has to be present because A is a vector. So we find a vector here. This is polarization vector. Right. It is important to understand that the polarization vector can only be perpendicular to the to the can only be perpendicular to the direction of propagation. Why is it so? This is set by our gauge, so supposed to be 0 via Coulomb gauge. If I write it in K representation, I just get K times A of K, which has to be 0, right? Which means that this vector has to be perpendicular to K. Good. That gives us 2 independent vectors, 2 polarizations. If these vectors were real, it would be very simple. It would be like we go to Z directions and we have X and Y. These vectors can be complex, so there's circular polarization as well. But okay, let's not talk about this. Let's just choose this polarization as in some way. And remember, there are 2 possible choices. To be independent, we just set vector product of these two. They have to be perpendicular vectors as well. Right, so that's why we can have all solutions. We have all possible cases, and for each case we have two parallelizations. Right. Good. So I now we have general solution. And now I switched from amplitudes A to something which again looks ugly. I introduce these and ugly coefficients. It's impossible to memorize. Don't you try. Again, it's good that we have it there. It's for the same reason that we have it in the elastic string. They make the Hamiltonian simpler. It's a rescaling of the Hamiltonian in such a way that for each mode, the coefficient here is just frequency. Fine that we dealt with. It's interesting to get the same expression for the flux. Then we get indeed something in the direction of a vector pointing into in the direction of propagation, which is logical. Electromagnetic wave, yeah, it pulls energy in the direction of propagation. There's energy flow in the direction of propagation. Fine. So we did the job. We have found normal coordinates. We can do usual game. Again, it's standard. It's the same for all possible oscillators, all possible physical situations. We make real coordinate and real momentum, which is associated with imaginary part of these coordinates there. With this, we managed to bring the Hamiltonian of electromagnetic field to a standard form. Right? No wonder that equations of motions are the same as for any Hamiltonian. And as promised, owing to linearity of the series, these equations are independent. Each harmonic oscillator labeled is discrete K and two indices for polarization. Each operator, each oscillator of the set oscillates independently. Very good. Boring part is over. Some rather important questions which will become practical later when we really would like to integrate overall possible electromagnetic excitations. And what I put here, just how many oscillators are there, right? How many oscillators are there per volume? There's a big volume with L. volume in coordinate space. There is a small volume in K space. And I would like to know how many oscillators are there in this volume. We have counted this for particles. Very same formula is for fields. Good. Here I have 2 pi to the third, and there's 2 of polarization. That's why I have here. More interesting and the practical formula is instead of volume in K. All right, in the same space, let me introduce a spherical system of coordinates. And I want to compute how many oscillators are there. Yeah, the radius in this space is related to frequency. So I want to compute how many oscillators are there in this volume of K space, which has dimension delta d omega. Good, so I just integrate this expression. That's what I have. That's how many oscillators per other in a frequency interval. Fine. When we sum up over this oscillators, we will do it in next lecture. Quantization. We will use this formulas. Let us see how much time do I have to explain single oscillator. Okay, that's about right. That's Maxwell equation is tricky business. What is easy to understand, what is easy to implement and apply are circuit theory representations of electric magnetic fields. Let me get for that. Let's me make just a simple electric oscillator. So I took capacitance, took inductance. Then I know for sure that there's a single mode oscillator, not infinitely many modes in the whole universe, but just a single mode. Fine. Let us understand how to make it as an oscillator set. This. Let me first understand that this oscillator has capacitive energy, and here I have voltage at the capacitor, and I have also inductive energy, and this is proportional to square of the current. Water equations of motions, I don't have to, I would derive it from the Hamiltonian, but I don't have to, yeah. Equations of motion, just circuit theory equations. First equation is just charge conservation. Right. The current is derivative of charge, but the charge at the capacitor is given by this. Oh, I've forgotten dot here. Good, and that is equation for the current. It's Faraday inductor. If you change the current in the coil, there's voltage difference in this coil. Right? You put these equations together, you get oscillator, which oscillates at this frequency. Fine. Let's make it a harmonic oscillator. We can do it in pretty, constructive way. We just take it as a purpose, and we got a hunch that momentum, right momentum, something moving, so perhaps it's proportional to the current. And coordinate, it's not charge anymore, it's coordinate, generalized coordinate is proportional to the voltage. Then we look at energy expression, and we immediately find generalized momentum, generalized coordinate for our oscillator. Combining those, we can find this normal coordinate, remember complex coordinate, which oscillates that nicely. Here it is. With this, we can kind of interpret field oscillators. We can estimate capacitance and inductance associated with each field oscillator in vacuum. Good, I did the job. So what I did today for a variety of classical fields, I have demonstrated that they can be seen as large sets of oscillators. Right, for all these oscillators, Hamiltonians are pretty much the same. And all physics comes into expression like this. So these D's are not specific for a physical situation. These coefficients actually define whether resulting field is displacement or vector potential of electric field or anything. All physics is in this relation for field in terms of normal coordinates. Right, so that was the message, I guess. That's what we know, sir. The purpose of this lecture was to refresh a bit classical physics, which is always good, and get this boring message. But again, it's not so boring. It enables quantization of everything, anything in any circumstances. Very good, sir. With this, let me finish my lecture.